A confirmation for the audio, please. If you're able to hear me out perfectly well, kindly confirm. Okay. So, till now, any issues that you have faced? Okay, perfect. Yashika, the land that we live on, how did that come into existence? Due to volcanic eruptions. You had volcanic eruptions that eventually led to the formation of the land. Okay. And then Dinesh and 2025 aspirant is practice test enough for next full year? Yes. As of now, just focus on the portion of this general studies along with the portion of current affairs. That should be more than sufficient. The practice tests will give you an idea about answer writing, the MCQ solving ability, all of that you will gain from that itself. Okay. Down to Earth magazine, Abhishek, should be looked at selectively. Certain particular portions. So, let's say in a magazine, you will have 2 to 3 articles which are relevant. So, that is something which should be studied at. A larger trend should be noticed wherever you find any particular point or a topic of current affairs in discussion. Take a note of that. Anushka, this class will continue till 8 p.m. Okay. So, now we continue further and we basically take a look at the written portion. Now, here, when we talk about it, basically, when we say the crust is the thinner and the thinnest outermost portion that we have, that is referred to as the crust. Okay, so it is the outermost solid part of the earth and it is brittle in nature. When something is brittle, means it breaks very easily. That is what is the meaning of brittle. So, whenever there is a kind of a stress, a kind of a duress, any kind of external pressure which is associated with it, that is when it breaks very easily. That is why brittle. Thickness of the crust varies when you consider the continental areas and when you consider the oceanic regions. The crust is particularly thin in the oceanic areas. The crust in the oceanic areas, here the thickness, mean thickness will be around 5 kilometers, 5 to 20 kilometers sometimes, whereas in the continental areas it is between 30 to 50 kilometers. However, sometimes the continental crust gets significantly compressed, as we observe in the case of the Himalayan region. That is where the continental crust has got significantly compressed, and that is where sometimes continental crust can be even as thick as around 70 kilometers. So it is thicker in areas of major mountain systems, as much as 70-kilometer thick in the case of the Himalayan area. Now, the oceanic crust, even though it is very, very thin, it is going to be heavier as compared to the continental crust. And that is owing to the density, the type of materials which make it up. Oceanic crust generally has got a density of around 2.9 to 3 gram per centimeter cube. Right? Continental crust generally is made up of granitic rocks, has a density of around 2.7 gram per centimeter cube. And the oceanic crust is made up of basalt, a dark colored rock which is richer in iron, magnesium, etc. And that is where the density is close to around 3 gram per centimeter cube. This is one of those facts which is mentioned incorrectly in the NCRTs. So while you are studying the NCRTs, this is an incorrect fact which is mentioned here. Okay, so in NCRT, you will find that oceanic crust is being allotted a lower density. No, oceanic crust will always have a much greater density, right? So here, how is it that both of them, even though oceanic crust is much thinner, is always going to be heavier? Always understand, oceanic crust is thinner but much heavier than the continental crust. than the continental crust. Okay, it is much heavier as compared to the continental crust, and that is because of difference in density. So if you have to understand this analogy, the understanding of this, the analogy can be very simple. Think about it as if you have a very thin slab of, let's say, iron, right? Let's suppose you have a thin slab of iron. Then on the other hand, you have a very thick piece, a very thick block of thermocol, right? Let's say this is thermocol and this is the sheet of iron. Now you would come across a situation where, regardless of the fact that iron is very thin, you'll find that this iron sheet is going to be substantially heavier, always. And despite the thickness, thermocol is going to be lighter. Why? Why do you think that difference in weight happens? Because of the difference in density. Due to difference in density. In density. Okay, so that is why you will come across a scenario where, regardless of how thin the oceanic crust is, it is always going to be heavier. This will have its connotations and implications when we come to the movement of the various different crust and the kind of landform which are created in the process. That is when we will take the utilization of this particular concept. Okay, Yashika, I see your question. But what I would request, not only to you, but everyone here, if you have pasted a question, wait for the reply. The reply will come. At max, if you are getting very impatient that this is a major question which needs to be addressed by the Prime Minister himself and this person is not taking it seriously, at max, paste it twice. Okay? The more you bombard the same questions, the chances of that will be being ignored will be much greater. Okay, so let's have that kind of a decorum from now onwards for the entirety of the module. Paste this question once so that even the SMEs will get an opportunity to take a look at your question. I will also address your question. This doesn't seem nice where you spam it out. Okay, so your question is, so all the times when the questions are pasted, there is some change in the question, but the more or less the question is, why and how come oceanic and continental land is different when both are created by volcano? Fair enough. Both are created as a result of volcanic eruption, but even that volcanic eruption which happens, the material which comes out, that is different, right? It is not as if in all the volcanic eruptions you will have the same materials which are ejected. If you think about it, or if you talk about it, even these eruptions, when we talk about, and volcanic eruptions and the outflow of lava, when we talk about, here you have to understand that the broader classification is andesitic lava, basaltic lava. Andesitic, which is generally felsic in nature, it has got rich content of silica in it, which is lesser in density. So that silica does not flow easily. That tends to accumulate one on top of each other. So eventually it will create a situation where it will emerge above water and create those lighter continental land masses. Whereas you have some volcanic eruptions where you have a very fluidic lava which comes out. We will study about all these in the portion of volcanic eruptions. You have very fluidic lava which comes out, which has, once cooled down, it is very, very dense. For example, you have the basaltic lava, right? Now, that is also what is the mafic lava in general, which is rich in iron and magnesium. It is not as if this basaltic eruption will happen only underneath the ocean floor, but because they are able to spread very easily, that is why you will find them to predominantly have a low feature landscape. They won't accumulate on top of one another. For example, when we talk about the Deccan traps in India, the region where you have the black soil, they have been created as a result of the basaltic lava. That is what makes that particular region particularly heavier. And because of that region becoming heavier, you have some of the implications where you have creation of rift valleys, block mountains in the region of the Deccan Plateau of India. Okay, we will come to all of that slowly and steadily. Don't worry. But here, you also have to understand that once you have the type of materials which immediately go underground and they go to a particular depth, that is when they melt, that is when the magma comes out. That also in significant processes that determines what kind of material will then erupt out of volcanic eruption. So that is where the type of materials in a volcanic eruption, they are never going to be same. They are going to vary in terms of the mineral presence. And each of the lava which spreads out, it has got its own kind of density feature. So that is when you have creation of lighter land masses or lighter crust and also heavier or denser crust. Okay, is that understood? Good. Now, after this, we come to the portion of the uh, area or in the structure of the planet immediately underneath the crust, and that is the mantle. The mantle extends significantly to the lower region, almost up till a depth of around 3000 kilometer. That is where you have the presence of mantle. Now, the portion of mantle is present immediately to the where the crustal portion ends. That is immediately around 50 kilometers from the surface, the portion of the mantle starts extending. Now, mantle is a highly compressed portion. It is solid, having a higher density, but it does not have that brittle nature. Beyond a depth of 400-500 kilometers from the surface, beyond that depth, it is absolutely something which is so compressed that things slide over one another. It will not lead to breakage or the breakage of the structure of the mantle. Now, this mantle consists of majority of the weight that we have in the planet. So here, portion of the interior beyond the crust, that is called as the mantle. It represents 68% of the Earth's mass. When we talk about the crust, whatever we see around us, the mountains, the land features, everything which is included in the crust, this manages to represents 1% of Earth's mass. Only 1% of the Earth's mass is represented here. And here, when we talk about the portion of the mantle, it represents 68% of the Earth's mass. So think about it. Whenever you would have come across a mountain, whenever you would have come across a hill, immediately the perception is nothing can be as gigantic as what it is. Nothing can be as grand as this is. And nothing can be as heavy as. That is why we say moving a mountain as a kind of a hard work, right? But imagine if I tell you that it is the lightest portion in the interior of the planet. So rest is left up to your imagination that what is present in the interior and what is the density of that material. Now, it has a density of around 3.4 gram per centimeter cube, and that density increases as we move significantly to the region of the core. So this density increases as we move to a greater depth. Why? Why is it that density indicates an increase? because there is going to be increased compression from top, increased pressure from top. So that is where the materials, they will morph themselves, the materials will get further compressed, and that is where the density would significantly increase. Okay. Now, the upper portion of the mantle, that is called asthenosphere. The word astheno in itself means weak, and it is considered to be extending up to a depth of 400 kilometers. It starts from a depth of around 160 to 200 kilometers, and that is the entire stretch, right? It is the main source of magma that it finds its way to the surface during volcanic eruptions. Okay, so when we had talked about the portion of the crust, let's say this is the portion of the crust. Now, underneath it, you have some amount of solid upper mantle. At a depth of around 160 kilometers to 200 kilometers in certain cases, let's assume 160 kilometers, that is when the asthenosphere begins. And this can have a depth up till around 400 kilometers. This is your asthenosphere. Okay, asthenosphere. And that basically indicates a weaker portion where materials are not exactly liquid, they are not exactly solid, they are semi-solid. Plasticky means it can be stretched. It can experience a kind of a stretchability of sorts. So not a perfect liquid, not a perfect solid. This is where in asthenosphere you have semi-solid, solid, plasticky state. I hope we understand the difference between elastic and plastic. When you deform an elastic, it will get back to its original position. When you deform a plastic, it will not get back to its original position. So that is the plasticky state that you find the asthenosphere in. Then we have the core. Now, core is the innermost portion. It is also divided into outer core and inner core. So, core mantle boundary is situated at a depth of around 2,900 kilometers, and core makes up around 31% of the planet. Inner core is in solid state, whereas the outer core is in liquid state. Why is it that the inner core is in solid state? Because of due to extreme pressure exerted from top, which does not allow the materials to expand. Okay, it doesn't allow the materials to expand. So that is why it remains in a superheated solid state. Now, core is made up of very heavy materials, mainly constituted by nickel and iron, and hence it is also referred to as the Nephe layer in general. Okay. Now, here, when we talk about the interior and the structure, as we start going into the depths, you will observe that the material density changes as one moves into the depth. The material density indicates a significant amount of change, right? Closer to the surface, the density is less. As you move greatly to the distance and into the depth, the density will change. So that is the situation which is present all through the interior. So basically, within every layer, you will come across a particular portion from where suddenly the material density, the type of distribution of substances, the property of the material, that changes. And they are referred to as discontinuities. So they are referred to as discontinuities. Discontinuities basically demarcate that particular area where you have a significant change in the material density, material composition, material property, expansion, contraction, elastic, plastic property, all of that changes. Now you have various different discontinuities which demarcate the differentiation between the different layers. So all of this is not very important for your examination, but you should be aware of it. For example, you have the Conrad discontinuity that separates the upper crust and the lower portion of the crust, because the lower portion of the crust has greater density. Then you have the Mohorovičić discontinuity. Mohorovičić discontinuity basically demarcates the difference between the crust and the region of the mantle. This is also what is referred to as simply the Moho discontinuity or simply the Moho. Okay. Then you have the Repeti discontinuity, which demarcates the difference between the upper mantle and the lower mantle. That is differentiated by what is the Repeti discontinuity. Then mantle and core, that is basically differentiated by what is referred to as the Gutenberg discontinuity. Now all these names are given by the individuals who have found that there exists a kind of a discontinuity. So that is how the naming is done. So you have the Gutenberg discontinuity, and then you have the Lehmann discontinuity. Lehmann discontinuity is basically the one which differentiates the outer core, the molten outer core, with the solid inner core. After all, it was Lehmann who came upon or who chanced upon this kind of a discovery that inner core is made up of a material or of a density which is very different from the outer core. Hence, the discontinuity was named as Lehmann discontinuity. Okay, so for your general studies, two of the discontinuities are important to know for your prelims perspective, that is Moho and Gutenberg. Both of these discontinuities are important for you to be aware of. In general, all of these, they are relevant for your prelims. Okay, so I understand the basic question which will come from your end is that, is it important to study this? It is important for your prelims perspective, but put significant concentration on Moho and Gutenberg. Moho is what? What differentiates the portion of the crust from mantle, and Gutenberg is what differentiates the mantle from the molten outer core. Okay. Now, discontinuity. Prashant, discontinuities are those particular demarcated areas or those particular areas of differentiation where suddenly, due to the high pressure exerted, etc., the type of rock densities, the property of the rocks, the elastic property, the deformation ability of the rocks, all of that indicates a sudden change. That is what is referred to as a discontinuity. Okay, so across the interior from the surface right up till the center, in that entire region, you come across many significant amount of discontinuities. Okay, now after this, we come at another portion which is basically sometimes asked in the prelims examination, and that is the minerals in the interior of the earth, the mineral distribution in the interior. So this is something which is relevant for your or important for your prelims and the prelims examination. So when we consider the earth as a whole, right? If you consider the entirety of the planet, iron, oxygen, silicon, magnesium, then sulfur, nickel, calcium, aluminium. So here, ideally, you should remember the top four. The top four should be known. Now, how come oxygen is present? So this oxygen that you see forming the part of the entirety of the planet, do you think it is the atmospheric oxygen that we are talking about? Or do you think it is something else? What do you think? Where do we get this oxygen? Or this oxygen is a part of what? Very good. It is in the form of oxides. So this oxygen forms compounds with various elements, various other elements as oxides. Okay. Then when we consider only the portion of the crust, the portion of the crust is dominated by the lightest materials of sorts. So you will have oxygen, the oxides, silica, alumina, etc., silicon, aluminium, iron, right? Then you have calcium, magnesium, etc. So that is where again the top four should be looked into. The top four should be analyzed and the top four should be remembered for your prelims. So it is different in terms of the entirety of the planet and different in terms of only the surface or only the crust. So only the crust, oxygen, silicon, aluminium, iron. The entirety of the planet, iron, oxygen, silicon, and magnesium. Okay. Now, after this, we come to the portion of rocks. Now, when we talk about rocks, that is something that you encounter on a daily basis, isn't it? When you step outside your house, you would be able to observe some or the other rocks. Now, what are these rocks? Rocks are basically what you will come across as aggregates of various different compounds, of various different substances taken together, right? So these rocks basically are an inclusion of various different compounds, various different materials taken together. Now they are formed differently. All the rock types that we have, primarily the rock types are divided on the basis of their formation. So you will find that the rock types, they are classified differently based upon their origin. Okay, so here this is going to be important just to know the basics. That is important both for your mains and the prelims. So here, when we talk about rocks, what are these? So they are mineral aggregates with a combination of properties of all the various mineral traces in them. Any unique combination of chemical composition, mineralogy, grain size, texture, other factors, they contribute to the property that we have, that we ascribe with these rocks. Now here, when we talk about the rocks, based on how they originate, you have the general classification based upon their origin. Okay. So when we talk about that particular kind of rock, just a moment. Yes. So when we talk about the types of rocks, these are basically classified on the type of origin. On the basis of origin. So on the basis of origin, how they have come into existence, you have the classification into igneous rocks, sedimentary rocks, and metamorphic rocks. Igneous. Igneous basically means that something which has got a kind of a fiery start or a fiery genesis to it, something which has been created as a result of fire, right? Something which is an outcome of something very hot. So these are basically formed as a result of solidification of lava or magma. I hope we are aware about the difference between lava and magma. Whenever you have a volcanic eruption which takes place, let's suppose in an area you have significant amount of volcanic eruption which takes place, molten materials, they start flowing out. So when the molten materials, they start flowing out, that is known as lava. Now these molten materials, they come from the interior, some portion in the interior, right? So when the molten materials, they are present in the interior, sometimes they can solidify there itself. And that presence of molten materials in the interior, that is magma. Okay, so when that molten material flows on the surface, that is what we refer to as lava, and when it is present in the inside, that is what is magma. So that is basically the genesis of igneous rocks. Now, igneous rocks over a period of time, now they will be exposed to the vagaries of nature, the various agents of nature such as rainfall, river movement, heating, cooling, etc. These rocks oftentimes over a period of hundreds of years, they will break into smaller substances and they will then disintegrate as small substances carried away by the river, small particles of grains, etc. carried by the river. They will be deposited somewhere. When they get deposited somewhere and other materials, soil, etc., that gets deposited, over a period of time, various different layers of these deposits, they are experienced. Right? Various different layers, they are deposited. These are, let's say, deposits. Now, these deposits, over the passage of time, these deposits will solidify. There will be pressure, compaction, cementation, etc. And they will solidify over a period of time. Solidifies. So this is formed as a result of solidification of deposits, right? Happening as a result of compaction. For example, take the case where you have a, let's say, a flowering pot, right? A garden pot that you have. Now leave some soil there without any plant. Put some other materials there, let's say broken or crushed stones, etc. Leave it out. After some time, you will find it turns into a hard solid, right? Imagine if it is left for hundreds of years and thousands of years, it will turn into a rocky substance. That is what we have as sedimentary rocks. Now, out of these two, that is igneous and sedimentary rocks, where is it that you think you are most likely to find the portion of organic material, that is the fossil remains of animals and plants? Out of igneous and metamorphic rock, where do you think you will find the presence of fossils or organic materials? Igneous or sedimentary, or both? Okay, so majority of you are absolutely correct. You will find the fossilized remains or the portions of these animal and plant remains in the case of sedimentary rock. That is where you will find that. Because in the case of igneous rocks, it is the molten materials which get solidified. So these molten materials, will they consist of animal or plant remains? No, molten materials are coming from the interior. So how will they contain animal or plant remains? So that is why sedimentary rocks, they still consist of significant amount of organic matter and fossils. Contain organic matter and fossils. Okay, that is something that you find in the case of sedimentary rocks. Then we have metamorphic rocks. It is basically derived from the term metamorphose, right? Metamorphose or metamorphosis is an English terminology, which basically means changing of property, changing of state, everything, right? That is metamorphosis. So when we talk about metamorphic rocks, so under conditions of high temperature or high pressure, this igneous or sedimentary rocks, they undergo kind of a change of state in terms of the fact that the properties of the rock types, etc., that completely undergoes a change, and that is what leads to the formation of metamorphic rocks. So these are the rocks which are created under extreme pressure or extreme heat, where the igneous or the sedimentary rocks, they are exposed to extreme heat or pressure. That is when the properties of the rocks, that in itself undergoes a kind of a change, and we have the case of metamorphic rocks. Let us take a look at the further details of it. Now, before taking a look at the text portion which is given in the slide, and before trying to rote learn it, observe the image of this igneous rock. This is your igneous rock. Now you will find a kind of a uniformity of structure here. The materials, they are present in a uniform manner. Now, why is that the case? That is the situation because they have solidified. The molten materials, that has solidified uniformly, and that is why you will find this kind of a material, where uniform distribution of materials, right? So the basic classification, now these igneous rocks, they are formed through the cooling or solidification of magma or lava. Now, obviously, when we talk about the planet, these were the first rocks to be created. And that is why these are also what are referred to as the primary rocks. Primary rocks. Because when you think about it, how is it that the rocks come into existence? It is basically created as a result of the cooling down process, where the magma or the lava cools down, and that is when the rocks are created. Now, those rocks can then get disintegrated, can break into multiple smaller portions, and so on. So that is where you have the situation of the primary rocks. So these are the first of the rocks which get created. Now, when they get disintegrated or they get compressed, etc., that is when you have sedimentary metamorphic rocks, etc., which are created. Now, primarily, they are classified into two types based upon where they are formed. If they get created as a cooling down of lava, that means if they are created and formed on the surface, they are referred to as extrusive rocks or volcanic rocks. If the magma underneath the surface, that in itself has solidified, that is something which has been formed in the interior. So it is the intrusive rock, or what is also the plutonic rock. So here, basically, igneous rocks may form either below the surface as intrusive or plutonic rocks, that is from cooling of lava, solidification of lava. And here, they can be formed on the, or rather, solidification of magma in this case. When they are formed in the interior, that is due to solidification of magma. And here, that is due to solidification of lava. Of lava. So that is what we have as the case of igneous rocks, the basic classification of the igneous rock, if you think about it. Now here also there are classifications: intrusive igneous rock, diorite, granite, pegmatite. Extrusive, they erupt on the surface and then cool down. Now, based on the minerals that they have, they are further sub-classified. So based on the minerals, present, they are further subclassified into what kind? That is, you have mafic, which are darker in color, denser, rich in iron, and magnesium. Then you have even ultramafic, where the iron concentration is even more, it is more heavier. So you have mafic, ultramafic. Then you have felsic. Felsic, that is lighter in appearance in general. This is what makes up majority of the continental land masses. So lighter, less dense, rich in silica and feldspar as well. Feldspar that you find on the surface and feldspar as well. So that is basically the case of the igneous rocks. Okay, you have ultramafic as well, which is further dark, greenish in appearance. Sometimes you will find that. So that is how you have the various different rock types. Now, in the case of intrusive and extrusive, let me ask you a basic question, which I want you to apply your logic. My tab battery is 6% left. Sadly, my dear friend, I do not have the ability to provide charging in a wireless fashion. Otherwise, I could have helped you out. But I hope you understand my limited capacity. If I would have been that kind of a magician, I could basically reach out and charge it. But I don't have that solution. So, all the best to you, right? ABC, this came agriculture, soil science. Yes, in basically this portion of rocks, eventually it is these rocks which will eventually break down, and that is how when these rocks will break down, that is what leads to the formation of soil. So oftentimes what is present in the rocks, that determines the fertility of the soil or the mineral present in the soil as well. Okay, now you can join from the website link, etc. also. Now here, let me ask you a simple question, which I want you to solve by logic. Intrusive igneous rocks are formed in the interior. Extrusive igneous rocks formed on the surface. Both of them, they are created as a result of the cooling down process, right? Molten materials, they cool down, both of them. Now, out of both of these, where do you think the cooling down process will be faster? One which is present on the outside or one which is present in the inside? Where do you think the cooling will be faster? Very good. Beautiful. So it is in the extrusive, that is the outer portion, where the cooling will be very fast. In the intrusive, because it is not exposed to the colder atmospheric condition, so cooling conditions will be very, very slow. So here, in this case, cooling is faster. Cooling is faster, right? Because it is in contact with the atmosphere. Now, when the cooling is faster, imagine you have a molten material. Imagine you have a molten material. It is cooling down very quickly. So, will the particles have enough time to form various bonds, linkages, and develop large crystals? No, they will not have enough time. They will start solidifying very quickly, due to which you will find that the grain size, the crystals, are very, very small. Okay. So that is why, because the cooling happens very quickly, you will find that it doesn't have enough scope to form multiple linkages and multiple bonds. So that is why, as the cooling is faster, grain size is much smaller. because it doesn't have enough time to form the various crystals. But imagine when we talk about the intrusive, where the magma in itself is solidifying, it will be a very slow process. It might take few years to solidify, right? So if it is losing heat very slowly, and if it is taking so much time to solidify, then the grains, they will have enough opportunity to develop the linkages, the various different linkages, isn't it? So that is where here you will find that the various grains, you will have larger grains, larger grain size. Larger grain size and larger crystals, due to which oftentimes you'll find that these are lighter, because many of the time, as the cooling is a slow process, gases will also come in, right? It will also penetrate, and that is how it will end up creating a lighter substance, larger grain size and larger crystals due to slower rate of cooling. What is grain size? What is grain? These things that you see, the small particles, I hope you are able to see. These are your what are referred to as the grains of the rocks. Okay. Now, then we come across the sedimentary rocks. Now, sedimentary rocks, they are created as a result of the process of deposition, right? So, if you observe this rock type, you will come across a scenario there where it has got various different kinds of materials. It is not homogeneous like your igneous rock. Igneous rock was very homogeneous, same kind of material. But when we talk about different types of rock, so here, or different types of materials forming a rock, observe, different materials have come together, and that is what is leading to the formation. So they are a resultant of deposits. They are a resultant of deposits. Of deposits. And when we say a resultant of deposits in general, you have to understand that this deposit can bring about various different materials. But where do these materials come from? Some or the other rock would have broken, some or the other actions would have taken to create these deposits. So, based on the source of deposits, sedimentary rocks are classified. Okay. Now, what do we mean by source of deposit? Do we mean that, let's say, from a mountain or a plateau, etc.? No. That is how these deposits have been generated. That is how these deposits have been generated. How the deposits are generated. Now, deposits can be generated due to certain processes only, either due to physical breakage of the rocks. The existing rock types, like an igneous rock, would have broken due to heating, cooling, action of the river, rainwater, etc. They would have broken into smaller pieces, created those deposits, which would have then accumulated to form the sedimentary rock. So it could have been the physical or mechanical breakage of rocks. Okay, or the deposits would have been created as a result of a chemical action. Which kind of chemical action? We'll talk about it. As a result of chemical action, or there would have been organic deposits which then had solidified. So, organic deposits. Okay, so that is where you have the classification of the rocks as clastic sedimentary, chemical sedimentary, and organic sedimentary. Let's take the example of all of these. For example, when we say clastic sedimentary rocks, so these rocks are formed from the mechanical weathering debris, for example, sandstone and siltstone, right? From the case of mechanical weathering debris, which is or residue which is created. So let's suppose you have a larger rock type which, owing to expansion, contraction, and so on, that rock has broken down into multiple smaller pieces, right? So it is the mechanical breakage due to which it is reduced to multiple different smaller pieces. Now these smaller pieces can then get deposited, and that is what creates eventually a sedimentary rock. Example, sandstone, siltstone. Silt is basically the deposit brought by the rivers. So that can also solidify over a period of time and form a kind of a siltstone. Now here, when we talk about clastic sedimentary rocks, always, most of the times, it is the existing rock which has broken into. But when we talk about chemical sedimentary rocks, the deposits are created as a result of some or the other chemical reaction. For example, here we can take the case of iron ore, limestone, etc. So basically, some or the other chemical reaction would have induced the formation. How? Let's take the example of the formation of iron ore that we find on the surface. So basically, when we consider the region of shallow water bodies where the water is not very deep, shallow water bodies, let's assume, where the water is not very deep. Now in this, you would have significant amount of water, but sunlight would be able to penetrate through. So when sunlight is able to penetrate through, you have the presence or you can find the growth of plants as well. Okay, various different plants. Now in that water, you have the presence of dissolved iron. Iron along with various nutrients such as calcium, etc., that is present in water. Now, when you have the presence of, let's say, elemental iron, it is dissolved in water. So, it is not present as a kind of a deposit. Let's say this iron is dissolved and diffused in water. And diffused in water. Okay. Now, here, it is not a deposit, but these plants, they carry out photosynthesis. So when they carry out photosynthesis, these plants, they will carry out photosynthesis. And when they carry out the process of photosynthesis, in that process, what do they produce? Produce oxygen. Now this oxygen undergoes a chemical reaction where oxygen combines with iron, reacts with the dissolved iron, right? And this oxygen undergoes that chemical reaction where you will find Fe plus O2 That gives Fe2O3, right? This is solid, a kind of an oxidation reaction. That is what is undertaken. Okay. So you have a kind of an oxidation reaction. So where you have solid. Now this iron oxide or ferrous oxide, this deposits, right? This is basically deposited and solidified as iron ore. Deposited and solidified as iron ore. Okay, that is what you find in the case of the presence of this chemical sedimentary rock, where a chemical reaction has resulted in the deposition taking place. Earlier, a physical breakage had taken the or has had led to the formation of these deposits. Right? Example, when we consider limestone. Now, limestone is particularly rich in calcium carbonate. Now, where it is formed? Again, in the shallow water bodies, all the shell bearing animals that you have, those shell bearing animals, basically the shells, they are rich in calcium and calcium carbonate. Now when they die, oftentimes those shells, they get deposited on top of each other and they are compressed, and eventually that leads to formation of limestone. So that is how these particular rock types oftentimes get created. Okay. Then when we talk about sandstone, by the way, sandstone is the main or the chief constituent of majority of the architectural construction and the architectural buildings that you come across of the Mughal era and later on. You'll find majority of them, they are made up of sandstone, be it Red Fort, be it Agra Fort, all of them, because it is very, very easy to basically carve out anything in that sandstone. So you could have very decorative motifs in that particular aspect. So the next time when you visit a Mughal architecture, observe the sandstone. It will have a very similar appearance like this. And that demarked difference, you will observe that during the time of the earlier rulers, that is the Delhi Sultanate, at that point of time, igneous rocks were used, like schists. They were used in order to carry out significant amount of construction. So that is why in the earlier construction during the Delhi Sultanate, you will not find many decorative carvings and mountings. But that changed, that started changing from the time of the Tughlaqs itself. That observed a kind of a change. It was further carried out with the onset of the Mughal Empire in India. Now, all these aspects you can observe firsthand. I always say that the easiest place to observe this is in the region of Delhi. If you happen to visit Delhi, I hope that you will visit Delhi at least during interview process. So, and I hope you get the opportunity to do that. So when you visit that region, there is the region of Hauz Khas, the Hauz Khas village, where you have significant amount of construction done by the various different rulers in that entirety of the period. So there you will find the difference in terms of the structure, the older structure which has got igneous rocks, and the newer structure which has got the sandstone. So that is where you will be able to observe the stark difference right next to each other. Right? You will observe that the older structure which have a grayish appearance, very simple, no decoration. Obviously, the architecture is basically defined by many other factors, but it was very difficult to carve anything out of them. Okay? Mysore also. Dikshitam, what in Mysore? Kanak is conch also a chemical sediment? No. Many of these conch shells, over a period of time when they get deposited, over a period of hundreds and thousands of years, they can then solidify into a kind of a solid rocky part, that is limestone. Okay. Now, then we come to the organic sedimentary rocks. Now, these are created as a result of the remains of plants and animals, the accumulation of plants and animals, when they happen to remain on top of each other, that is when you have the creation of these organic sedimentary rocks which are formed. So here you will find, for example, let's say forests and trees of forests. So when the trees die, in many of the cases when a lot of trees they die at the same time, they get deposited. They get deposited one on top of each other. And that is where the carbon part of these, they get solidified, and you have overlying deposits as well. That is when they get converted into materials like coal. Okay, so coal is something that you find in the portion of organic sedimentary rocks. Example, coal, formed as a deposit of remains of trees and wood. Okay, in Mysore, we can find buildings built by sedimentary rocks. Yes, my dear friend, you will find buildings built by sedimentary rocks across the country. Why I was referring to Delhi is because in that region of Hauz Khas, you will be able to compare the architectural differences indicated in igneous and sedimentary right next to each other. I'm sure whichever part of the country we belong from, we will have our own kind of sedimentary structures, own kind of igneous rock structures. So I hope we are not getting that FOMO feeling, right? So that was just a kind of an example that I gave you. Now here, then we come across to metamorphic rocks. Metamorphic rocks, basically here, they can be formed simply deep beneath the Earth's surface, subjected to high temperature and great pressure of the rock layers from above. So when the existing igneous and sedimentary rocks, when they are exposed to very high temperature, very high pressure conditions, that is when they change their state, they change their material density, they change their material property also. And that is what leads to the creation of metamorphic rocks. These metamorphic rocks, they will not have the property that is indicated by the original sedimentary or the igneous rock. They will have an altogether new property. Okay, so for example, limestone is a sedimentary rock. Limestone metamorphoses into what? What does it metamorphose into? It metamorphoses into marble. The marble that you use in construction, right? Taj Mahal. Other than that, also various other places have marble buildings and marble construction. So that is the case of metamorphic rocks. Now, few of the metamorphic rocks, they appear to have a kind of a layered structure, and few of them will have a very unified structure like that of the igneous. So accordingly, you'll find that the metamorphic rocks, they are divided into foliated and non-foliated. When we talk about foliated rocks, so they basically appear layered, and here non-foliated, they don't have the layered formation, they don't have the layered appearance. That is the primary difference. Now we come to the portion which we define as the rock cycle. What is rock cycle? So basically all these rocks, under the necessary conditions, under the prevalent situation and conditions, all these rocks have the ability to get converted into each other. All of them. Given the necessary conditions and exposure to the necessary situations, all of them, they can get converted into other format. Right? For example, take the case of any of them. Let's say we consider the primary rock, that is igneous rock. Now this igneous rock can be exposed to vagaries of nature, can disintegrate, and when it disintegrates, there will be weathering, erosion, etc. It will create lot of sediments, lot of deposits. These deposits can solidify to form sedimentary rocks. Now these sedimentary rocks can again break down, right? They can again break down quite significantly. And when they break down quite significantly, they will lead to again the formation of sediments. Again, these sediments can compact themselves, cement themselves, form sedimentary rocks. If these sedimentary rocks, let's say, are exposed to high amount of heat, high amount of pressure, they can get converted into metamorphic rocks. For example, when the crustal layer, which has a sedimentary rock, when the crustal layer that compresses itself, when the crust simply presses against each other, the pressure is so high that you have the formation of metamorphic rocks. For example, take the case of Himalayas. Now, amongst the highest peaks of the Himalayas, that is the greater Himalayas, the Himadri, the tallest of these mountains. At one point of time, majority of them were sedimentary rocks. In fact, in the region of the Himalayas, including the region of Mount Everest, around that area, you'll find the presence of limestone, which tells you that at one point of time, these rocks would have been underwater. But over a period of time, they have been compressed to such an extent. There's no water to be found anymore in that region, at least the kind of a sea or ocean, but it has been compressed, elevated. Much of those have been converted into metamorphic rocks. So that is where sedimentary rocks can get converted into metamorphic. Now that metamorphic rock, when it is created, that can also break down into various different smaller parts, and that also can form sediments. These sediments can again form the sedimentary rocks. Or these metamorphic rocks, let's say, with the circulation of the crustal layer, as we will study about it, that the surface sometimes that simply sinks or goes underneath the earth's surface because of the movement of the land, etc., and that leads to the melting of materials, and that can again lead to formation of magma, which can then lead to formation of igneous rocks. These igneous rocks under heat and pressure can get converted into metamorphic rocks, and that is where each of the rock type has got the unique ability to change the state, to change the particle size, to change the property as well. So that is what is referred to as a rock cycle, right? That is where each of the rocks have got a different kind of, or have the ability, under certain conditions they can always change that. Okay. If sedimentary rock is exposed to such high temperature and pressure, then does it still have fossil fuels contained in it? Not always so. See, even coal, when that undergoes significant amount of pressure, that starts getting converted into granitic form, right, which is much purer form of carbon. So not always so. Graphite rather, not granite, graphitic rocks. Okay, so-called the granitic rocks used in, it is a kind of an igneous rock, Nitin. It is the kind of an igneous rock which is generally um, intrusive in nature, right? And that is where the granite slabs that are present. So that is what is the, now even there you will have different colored slabs that you will observe. You will have light colored as well, you will have dark colored as well. So that depends upon the mineral composition. Okay. And Kirutiga, which rock is higher in density? Generally, you will find igneous rocks being higher in density, but there also you will have difference in densities, right? Then generally you will also find some of the metamorphic rocks, they are much more denser owing to the high amount of pressure. So it varies. Okay. For example, few of the granitic rocks, that is the continental rocks of igneous variety, they will sometimes be lighter as compared to few of the metamorphic rocks. So it varies. Is everything clear up till now? Or is there a portion which has been a bouncer which you cannot tackle? Let me know. Are we comfortable up till this portion? Yes? If not, feel free to ask a question. No issues in that. At max, what will happen? A couple of jokes here and there, but then that will continue. Okay? So if any issues that prevail, kindly let me know. We'll ask tomorrow. Okay. Tomorrow we don't have a session. You can mail it to me nonetheless. Okay. So now we come to the portion which UPSC likes to ask many questions from, both in the prelims as well as the mains examination, both for your general studies as well as for your optional area. This is a region where you will find a lot of questions to be appearing from the areas. For example, in this, we will study certain areas. First, we will study the continental drift theory. Continental drift theory. Then we will be studying sea floors, the convection current theory. We will form a kind of a chronology in terms of when they have been postulated. Convection current theory. Then we will be studying the aspect of seafloor spreading theory. And all these theories have finally led us to come to the understanding of the theory which is much more acceptable and which explains about the movement of the continents in the oceans. That is the plate tectonic theory. Now, out of these are the three important portions. Okay, under this we'll come across, under plate tectonics we'll come across various cases. For example, why is it that the region around the Pacific experiences so many earthquakes and volcanic eruptions? Why is it that the Himalayas were created, and so on? And why is it that in those regions we don't have volcanic eruptions? All those portions we will cover, we will talk about. But before that, we'll take a break. Okay, ideally I would have continued till 8, but I generally come across the scenario where candidates, they start giving up at 7:20 or 7:30, that now it is enough, please shut it down. So I will give you the final break. Okay, relax, splash some water on your face, whatever is required, before we delve down into the portion of origin of continents. I'll try to narrate it like a story so that it is digestible to you. I understand that you have been covering the session from the morning, so you also have limited capacity. I'll try to narrate it in a way where it is much more digestible, where it is retainable over a long run as well. Okay. Uh, can we say that crust formed during solidification are igneous rocks? Yes, Vishal, that is why we say that igneous rocks are primary rocks. In fact, that is the question which, and many of the sources of various coaching institutes that you find on the website, they are absolutely incorrect in this. The question was asked in UPSC 2022 mains, that is, what are primary rocks and its types? A very simple question. There you had to talk about why igneous rocks are primary rocks, what are the various types, what are the characteristics. That is it. A couple of diagrams would have done, right? Many of the candidates I came across who later get in touch with us after they have written, they have read somewhere else, and then they basically want to seek a validation from us that you tell me that my answer is correct, I'll be satisfied. Many of them, referring to different sources, had written that primary rocks are sedimentary also, metamorphic also, igneous also. That is not. Primary means first kind of rocks created, igneous rocks. Okay. So that is basically, is it necessary to draw a diagram for geography? More than what you feel, more necessary than anything else. Okay. So here we take a break, guys. The final break will take for 10 minutes. Recharge, replenish yourself, and be back. A confirmation for the audio, please, guys. If you are able to hear me out perfectly well, kindly confirm the same. Thank you. So now we come to the portion of origin of continents and the presence of various different oceans. Now here, slowly and steadily, as the advent of science and technology happened, as the world started getting smaller, not in terms of its physical size, but in terms of the reach, people were able to map out different areas, different continents, etc. That is when it was significantly intriguing for everyone to think about it, that why is it that the continents have a certain shape? Why is it that certain areas are together? Why is it that certain areas are far away from each other? So that is when, during the 1800s itself, you had the initiation of various different theories which began to be provided in the terms of providing the explanation. If the continents have a certain shape, there is a reason behind that, or so on and so forth. All the celebrated geographers and geologists, during many of them, for example, you had Lothian Green. Now, all of them, initially, they provided a kind of a theory that is contractionist theory, which talked about the fact that the planet, as we see, that is contracting. And as it is contracting, that is why you have the conical shape of the continents, oceans, etc. Now, these were celebrated geographers of the time. Now, what happens when someone that is celebrated, when they say something, it is always taken as a gospel of truth, that that individual is telling the absolute truth. But it was later all these were debunked, these ideas were debunked as to be absolutely false, that nothing of that sort is happening, the planet is not contracting, etc., etc. Now, in the year around 1907, that is when you had a geographer and a geologist in the name of F.B. Taylor. F.B. Taylor, for the first time, he propounded an idea that, look, the continents that we are standing upon, these continents can drift, right? He just propounded that kind of an idea, that it can drift. He did not propound a particular theory, he did not have a particular evidence, etc. He just postulated this. So he postulated the idea. Postulated means put forward. Postulated the idea of drift or movement of continents. Now, when you think about any particular theory, let's suppose you as an individual, you want to put forward a theory about the behavior of civil services aspirants. All of them indicate a certain unique kind of a behavior. They will have a fear of missing out, etc., etc. They will accumulate and hoard newer materials which they will never study. All of those kinds of things. Now, when you postulate or when you propose a theory, it has got various different stages. First of all, you require certain evidences based upon which you can put forward that theory. So you require the basic theory. What does the theory postulate? What are the evidences which support that theory? What are the assumptions that you have made? For example, the Big Bang theory. The postulation was that at one point of time, there was an explosion due to which everything is still expanding. Now, the assumption was that at one point of time, around 13.8 billion years back, everything was concised and condensed into a singular material. And then you give the reason why it would have exploded and so on. So that is included in a theory. So F.B. Taylor did not provide a very detailed theory. He just provided a kind of a postulation. Now, fast forward it to a couple of years. Now, around the year or era of 1912, That is when you had a German meteorologist with the name Alfred Wagner. Now, Alfred Wagner was a climatologist and a meteorologist. Alfred Wagner. Now, he was primarily a climatologist. That is, he would specialize in studying the climatic behavior, and he would study the past climatic conditions which would have prevailed in a particular area. He would oftentimes study the regions around Europe, and he would oftentimes base his study and would basically think about how the climate is changing over Europe. He would make significant number of trips to Greenland to collect the past ice pieces and the ice records in order to understand how the climate has been indicating a change in that region as well. So that was his primary role. But as the famous story goes, the famous anecdotal story as it goes, basically, it is said that one Christmas and on the eve of Christmas, basically, one of his friends gifted him a detailed world map. Now, world map in those days used to be a prized possession, a detailed world map. Nowadays, you have it present in the atlas, which we don't even open, which we don't even touch. But at that point of time, it was considered to be an accurate depiction of the world, was considered to be something of a fine artisanship and something which not everybody could do. Now, Alfred Wagner, upon receiving that gift of a detailed world map, he started studying the world map. He started exploring the world map. And basically, we are in the 1900s now. 1900s have been an era of discovery, of lot of innovations, lot of discovery in general. Now, there he stumbled upon something very unique. When he looked at the map, he found out certain areas. For example, he looked at the shapes here, right? The shape here, here, and here. Okay, the shape here and the shape here. So, while he was exploring the world map, he basically stumbled upon these shapes, and all of these shapes appear to fit into each other. So that struck him. It cannot be a mere coincidence. It cannot be the situation that the land formed in South America is having the exact same shape on the eastern side as compared to the western part of Africa. That is when, despite being a climatologist, he started exploring all the various different studies which had been done by the geologists of that time, by the paleontologists of those times. Paleontologists are the ones who specialize in study of fossils. So those are your paleontologists. He started carrying out a detailed study of all of this. And basically, at the end of it, he came upon certain starking evidences which all pointed to the fact that at one point of time, all of this would have been together and they have drifted away. What are those evidences? So, evidences, for example, the shapes would match. Evidences which indicated that at one point of time, southern part of India had the presence of massive ice glaciers. The region of southern part of Africa had the presence of the evidences which indicated at one point of time in history, millions and millions of years ago, this would also have been covered under ice. So he started wondering, how is it possible? How is it possible that these regions, they indicate the presence of these icy glaciers when in the present day scenario, you cannot even imagine that southern part of India will have the presence of glaciers. You cannot even imagine that. You cannot even come across the imagination that the southern part of Africa will ever have the case of presence of glaciers or ice. This could be possible only in two conditions: that the climate has changed so rapidly over past few years, few millions of years, that this region might have been frozen and now it is very, very hot. Or the other possible reason could have been that at one point of time in history, all of these would have been together and they have later on separated. So, based upon the set of evidences of fossil records, based on the evidences of climate change, etc., he propounded what was referred to as the continental drift theory, or theory of continental drift. Now, because he was able to propound that, because he had very unique set of evidences which were not studied, all of these evidences were present separately, because the geologists had studied something, paleontologists and the botanists had studied something, but nobody cared to compile them and look at the larger pattern which was indicated. So that is why, based on the set of evidences, he propounded a theory. What was that theory? The theory was that, look, at one point of time in the history of the planet, you had a situation where all the land masses were one large land mass surrounded by one unifying ocean. He named that landmass as Pangaea. And he named that water body which surrounded it as Panthalassa, or the ocean of the world. Panthalassa. In fact, he went further on to say that the present day Pacific Ocean is nothing but a remaining portion of that Panthalassa. Then he said that this Pangaea would have broken into two portions. These Pangaea would have broken into two portions. The portion to the north is what he named as Laurasia. And the portion to the south, that is what he named as Gondwana land. Gondwana land. Okay? Then he said that these further broke. These further broke in a scenario that you have the present day shape of the continents and the oceans that you have. The present day shape of the continents and the oceans that we have. Okay. Now he came across the impact, or he came across the set of evidences which indicated to him that at one point of time in the history of the planet, everything was significantly joined with each other. And now they have sort of moved away. Basically, he came across an evidence which indicated that North America at one point of time was joined with Europe, South America at one point of time was joined with Africa, and they are moving westward. Right? They are moving westward. Then another evidence pointed to him the fact that at one point of time, Africa, India, Australia, South America, all of them, because they had the presence of ice and glacier, that indicated that they would have been present very close to the region of South Pole, and they have moved away from poles. They have moved away from poles. So, this was his theory that he said. And as per his theory, he indicated two types of movement. One is what he referred to as a westward drift, indicating the movement of North and South America away from Europe and Africa respectively. And the other was the movement towards equator, that we see where India has moved towards equator, Africa has moved towards equator, Australia has moved northwards, etc. Now, he was a climatologist. He had basically studied the evidences provided by the other people. So obviously, he did not specialize in providing these kinds of explanation that why this movement happened. But you cannot have a theory without providing a proper explanation to it. So that is when he borrowed from the works of Edward Seuss and other various geographers. And he provided some reason. He took in certain assumptions and then he provided some reason, right? Some reason in the aspect of why is it that the land is moving? Why is it that the continents are indeed drifting? But those reasons were absolutely imperfect, they were false, and they did not stand the justification of logic. But then he managed to publish that entire theory in an essay, a detailed essay, which was published in German around the time of 1912. It was published in German, so obviously it was not accessible to the rest of the world. Then World War I broke out, and obviously Germany was not taken upon kindly. Germany was not looked upon as kindly as possible. It was looked down upon. Around the 1920s, around 1925, his explanation and his entire theory was published in English. Now, people, they started laughing off at the theory that is provided because for the first time, someone had talked about the fact that these massive lands and the continents that we are standing upon, that indeed can move. Someone for the first time talked about the possibility that this landmass that you talk about, this landmass that you always kind of think about that this would have been present, there is God's grace, etc. This landmass has come from somewhere else. The geographers were not ready to understand that or not ready to even think about that. All of them, they looked at the reasons, the imperfect reasons that Wagner provided. They laughed it off. So much so that during the 1920s, the entire geological and geographical community was divided into two parts: the drifters and the so-called non-drifters. Now, drifter has got another English connotation associated with it, but in this case, drifters would be those who would adhere or attest to the fact that yes, indeed, there is a possibility that the lands could drift. Now, obviously, this is a theory provided in Germany. So you can think about the reaction which United States, which was one of the leading luminaries of discoveries at that point of time. Everybody in United States, they started boycotting these drifters. And nonetheless, during the entire process, Alfred Wagner was laughed off, was made fun of, and he was not included in majority of the discussions overall because he was thought to be a kind of a lunatic to have the guts to even propose this. He was admonished, and eventually Alfred Wagner, by that point of time, obviously, he had propounded his theory around 13 years, 14 years back. He carried out with his normal study of climate. And it was during one of those trips to Greenland where he met his sad demise. He died. Now, till the point that Alfred Wagner died, his theory was not accepted and he was ridiculed. It was only much later, almost 40 to 50 years later, when the newer discoveries based upon the study of earthquakes and the regions where the earthquakes occur, when the plate tectonic theory was propounded, then it was understood that look, the theory that he provided, that theory was correct. But the reason that he provided, those reasons were incorrect. And that can happen because you are not a geologist from the profession, you are a climatologist. You don't specialize in the interior of the planet or the study of the earthquakes, seismic waves, etc., which give you an idea about the interior. So that is why the reasons and the justification that he provided to prove his theory, that were absolutely imperfect. But nobody can deny that for the first time, it was Alfred Wagner who showed the world the possibility that yes, indeed, this continents can move. Because always think about it. Think about the fact that if somebody tells you that you can have a device which can fly, now that opens up your mind to that kind of a possibility, and you will then work towards making that device which can fly. But even though you are an inventor of the airplane, immense credit lies to that individual who first of all opened up that idea of imagination. That is why even in the present context, when we talk about the contribution to the plate tectonic theory, the contribution of Alfred Wagner, who for the first time opened up the possibility of drifting of the continents, that can never be ignored. Even though he never received credit for that during his lifetime, it was much later in the 70s and the 80s. That is when the real value of this continental drift theory that was understood. This continental drift theory was rejected because of its drawbacks, but the evidences that were provided, that were solid, and those evidences all indicate to only one possibility, that at one point of time in the geological history of the planet, all of these places would have been one landmass and they have divided over a period of time. So here we'll take a look at the theory provided by Alfred Wagner. We'll take a look at the evidences that he provided, the assumptions that he took in to provide the reasons, and what were the reasons which were so absurd that it was not only incorrect, he was ridiculed, laughed off, and the theory was rejected in the process as well. So we'll take a look at the entire process. Okay? Shivani, the theory given by Alfred. Yes, if we are dealing on the first name basis, so yes, the theory provided by dear Alfred, that was correct, but it was rejected because of the reasons and justification provided by him, right? But the theory in itself, what it tried to say, what it tried to convey, that theory in itself is more than correct. We will take a look into it and we will study about it. So basically, Alfred Wagner, he based his evidences, right? He based his theory on the various evidences. What was the first evidence? The first evidence was the jigsaw fit of continents. This was a kind of an evidence which was indicated just by the physical appearance. So here he found out that the regions that we talked about, for example, the eastern coast of South America, the western coast of Africa, here the coast of Horn of Africa, here the case of when we talk about the coastline of the Arabian Peninsula, when we talk about western coast of India, when we talk about the region of Madagascar, when we talk about the region of Australian coastline and the region of Antarctica, all of these have a significant similarity in shape. So he concluded that, look, you cannot have so many coincidences to come true at the same time. More or less, it would have been a situation invariably where these would have been one at one point of time and they have drifted away, they have moved away. Then he based the evidence on certain aspects of geological structures. So basically, he came across certain factors where, for example, when we talk about, he observed that there is a significant geological similarity in existence of the rocks that you find, the rocks when they are formed, the rocks when they are created. So basically, the rocks, if they are created at the same time and the same place, they will exhibit and indicate a similarity of structure. They will indicate a similarity of origin as well. So he found that the rocks that you find in the Appalachian Mountains are present on the eastern coast of United States, right? So these are very old mountains, roughly around 250 and more million years back. So the rocks and the geological origin, the structure of the rocks in the Appalachians, they are very, very similar to the rock formations and their origin that you find in the Scottish Highlands. It cannot be a coincidence that the same structure, same property, same density, same material presence that is found across the ocean, separated by tens of thousands of kilometers. Again, he found or he came across a situation where the rock types that you come across in the region of eastern part of South America and the rock structures that you find in the region of western part of Africa, they bear a significant amount of similarity as well. So that again points to the fact that these would have been together at one point of time in the history. Not only this, he also came across the existence of glacial deposits. Or before glacial deposits, he came across the placer deposits. Placer deposits. Now, what are placer deposits? Deposits which are placed far away from the source. For example, let's suppose you have a mountainous area which is rich in mineral, significantly rich in mineral. Now, let's suppose here you have a river which is flowing. A river which is flowing here. Now, here, basically, let's assume that we consider this. Now, here, let's assume you have the presence of a material such as gold. Now, gold is insoluble in water. Let's suppose here you have the gold. Now, this gold will be picked up, right? This will be picked up by the water. Now, slowly and steadily, one particle at a time, this would be picked up. The river would drain it. River will have enough speed to carry it forward as well. Eventually, the river will start depositing it. Right? So, in majority of the regions, the gold that you find are in the form of the deposits around the rivers. Example, when we talk about river Subarnarekha. Subarnarekha, which moves in the region of Jharkhand, around the area of Jamshedpur, Ranchi, etc. Now, that particular river has at one point of time, the name Subarnarekha itself is because it is referred to as the golden line. It would carry a lot of gold deposit along with it. Now, these deposits that you see to be found in this area, now these deposits have not been created originally in this area. These deposits have been driven down from here all the way to this region. So that is why these deposits, they are referred to as placer deposits. Placer deposits. Now this is where this is referred to as the source rock. This is what is source rock. So, for every placer deposit, there needs to be in existence a kind of a source rock, right? So, for every placer deposit, there has to be a source rock. Now, here, understand this. Without the source rock, you cannot have placer deposits. Basically, if I take you back to the map, here in the western coast of Africa, around Ivory Coast, Ghana, and these areas, you have lot of placer deposits of gold, right? But you don't have any source rock in this region. You have lot of placer deposits here. Upon further investigation, it was found out that the same gold type, the same variety that is found in the rocks here in the Brazilian highlands. So that means here you have the placer deposits, and here you had the source rock. So obviously, you cannot have a situation where this source rock will be eroded and carried by the ocean and then deposited 10,000 kilometers away or so much distance away across the region of Africa. You cannot have that situation. That can happen only when this would have been together. That is when you would have had a scenario where this source rock would have created the placer deposits in this region, isn't it? That further bolstered his idea and the fundamental that this would have been together. Then you had the case of glacial deposits or the glacial evidence. Glacial evidence is divided into two parts. One is the glacial deposit. So when the glaciers move, these are massive chunks of ice. These are very, very heavy. No other agent of nature has got so much tremendous amount of force and weight as the glaciers themselves. So that is when the glaciers, they move, they deposit very fine particles which they would have eroded in the way that is referred to as glacial till, or what is referred to as tillite deposits. Okay, that is the glacial deposit. Now these glacial deposits, they were found in many areas of the world where presently you don't find any glacier at all. For example, the peninsular part of India, the southern part of India, no ice present at all, but you have glacial evidences there, right? Even for that matter, Aravalis have glacial evidences, which indicates that at one point of time, Aravalis would have been so very high and it would have had the presence of glaciers significantly. Then the southern part of Africa, that also has got. Then southern part of South America, southern part of Australia. Then the other evidence is the glacial striations. Glacial striations. Now, striation is again an English terminology. You would have come across this while you read various things. Striations are basically linear markings of sort, very linear markings. So when the glaciers, they exert a weight on the base rocks as they move, they end up scratching the rocks and they create a unique kind of a scratch mark. So when we talk about glacial striations, observe here. Observe these kind of linear scratch marks, very linear, as if some artificial agent has done this. So this is a remnant on the rock, markings on the rock, which indicate the movement of glaciers at one point of time in history. So striations, basically, glacier striations mean linear markings on the rocks which indicate a movement of glaciers at one point of time in the history. In history. Okay, so that is glacial striation. Now, where were these found? Now, these glacial striations, basically, if you would observe, they have been found to be present in southern part of South America, southern part of Africa, portion of India, southern part of India, and the southern part of Australia. None of these indicate any kind of glacial presence as of now. But if you somehow jumble them all together, it perfectly aligns around the region of South Pole, where it would have been attached with Antarctica as well. So that again further fortified his point that all these land masses would have been together, they would have moved away. But not only this, he was further assured of this particular fact based upon the study of the fossils, the paleontological evidences. Now, based upon the paleontological evidences, he came across certain fossils which were spread over various different areas. For example, Mesosaurus, the most remarkable of them. Now, Mesosaurus is an evidence of a freshwater reptile. Freshwater reptile which can grow from around 7 to 10 feet, which would be found in shallow waters, right? Some amount of river waters, etc. Now, these evidences or the fossils were found in South America as well and Africa as well. Now, here, how is it possible that simultaneously you have evidences of this animal to be present in different areas? Same is the case with Cynognathus, same is the case with Lystrosaurus and Glossopteris as a plant as well. All of them were found to be spread across multiple continents. So that again indicated these would have been together. In fact, he went a step further in this, and there he had studied the various different features or the behavioral aspect indicated by lemmings. Lemmings are the very small animals, like a rodent of sort, an enlarged rodent of sort, that is found in Scandinavian region to the northern part of Europe. Now, lemmings exhibit a kind of a very unique behavior, where in the case of adverse conditions, they all run to the west, right? And what lies to the west of those Scandinavian nations? Water. That is where many of them, they fall to the death, right? Now, Alfred Wagner said that, look, it cannot be a random occurrence that lemmings, all of them, are running to the west to jump into water. Water is available everywhere. If they want to jump in water and kill themselves, they can kill themselves anywhere. Why are they all running to the west? Wagner propounded they are running to the west because in their collective conscience, in their collective memory, they are still following that kind of a memory where there would be land to the west, and that land basically has now drifted away to the west. That is why you have water in between where they are dying. So like this, he had multiple set of evidences, and based on these evidences, he proposed a theory. The theory he proposed was that there was a huge landmass which was known as Pangaea, that was surrounded by the water body or the ocean of the world, which he named as Panthalassa. And basically, that Pangaea or landmass got divided and separated, right? It broke up to form different continents, and continents drifted away to form the present shape. Now, the continents, when they drifted away, he basically, all the evidences that he had collected, that indicated two kind of movement. That once North America was joined with Europe, South America was joined with Africa, now they are moved away. So he wanted to prove two movements, that is westward drift of continents, and also he wanted to prove that at one point of time all these countries or all these continents of Gondwana land, they were closer to the poles, they are moving away from the poles towards equator. So movement away from the poles, movement away from the poles. Okay. Now, in order to prove this, basically, he had to take some assumptions into place. In order to propound the reason, he had to take some assumptions, right? Now, before these assumptions, as per this theory, Wagner also postulated the fact that look, as the continents are moving, as the continents are drifting, they are encountering the oceans, right? As the continents are moving westward, they are basically encountering the oceans. And due to that obstruction and resistance provided, the continental landmass as it is moving, it is getting folded. So that is why he said that across the coastline of the continents, you have the presence of fold mountains also, right? So with the help of this theory, he could explain the fact that you had basically the presence of various fold mountains in that area. So with this, he said, as continents moved to the west or over oceans due to obstruction, the crust, continental crust, folded to form mountains. And he also said something which was very interesting, which for the first time someone tried to explain. Because till that point of time, geographers were not able to explain why is it that you have the presence of island arcs. That is, you have chain of islands here, here. Why is it that you have these chain of islands? Nobody could explain that. So here also he had an explanation that look, as the continents are drifting, the entire landmass is not able to keep pace. So small land masses, they keep on breaking and they form the islands, right? So that is where he could explain the formation of the fold mountains. He could also explain that the formation of islands. That is, even though this was incorrect, but nonetheless, he said that as the land moves or as the continent moves, some portions are unable to move at the same speed, and break to form islands. Okay, they will break to form various islands. That is basically the proposition that he gave. Right. Now here, let us take a look at the reasons that he cited. Before that, we'll take a look at the assumptions that he made. He made certain assumptions to justify the reasons. So assumptions made by Wagner. What were the assumptions? So the first assumption that he made was about the interior. The idea of interior was completely borrowed from what was given 60 years earlier by the Austrian geographer, that is Edward Suess. He was a very celebrated geographer of his times. So he simply borrowed the idea about interior from Edward Suess. Borrowed idea about interior from Edward Seuss. Right? As per the assumption, he said that look, the interior is classified into three regions or three zones. That is what you have as Sial. Sial refers to the silica and aluminium. Silica and aluminium. And this he said as the continentals, or the things which make up the continents. And then the middle layer is what was referred to as Sima, that is silica and magnesium. Okay, this he took as the case of the mantle, right, or the oceanic boundary or the oceanic surface, bottom. Then you have this Nephi. He took this kind of an assumption of the interior. Then the second assumption that he took was basically continents move freely over Sima, what he considered as the oceanic areas during that time, just like a boat moves on water. That is, as a floating object. Okay, as a floating object. Now think about it. Can that be possible? Can you have a scenario where the continents are floating freely? All of us, we are sitting on floating substances? Absolutely not. But this was an assumption he made. Now, these assumptions were made to do what? To justify the reasons that he cited. So, what were the reasons that he cited? So, the reasons he cited were two. First reason was the force of gravitation or the gravitational pull. Gravitational pull by moon and the sun. What he also referred to as the tidal force. And this was to prove the westward drift. To prove westward drift. And then the second reason that he cited was the combined action of centrifugal force and force of buoyancy. Force of buoyancy. Buoyancy, I hope we are aware. The force that you experience which keeps anything afloat, that is the force of buoyancy. So here, the combined action of centrifugal force and the force of buoyancy to prove what? To prove movement away from poles. Now let us take a look at these two reasons. First is the tidal force. What did he want to say by the tidal force? Tidal force. So his postulation was very simple, because the assumption was that the continents, they are moving freely, right? So that basically opens up a lot of possibilities. If the continents are floating freely like thermocol, that opens up a lot of possibilities. So he said that you have the planet Earth, which consistently is moving, and rotating in a west to east direction, right? And you have the moon. So he basically said that, look, you have the various different land masses which are present. Let's suppose the planet is consistently moving from west to east. This is the sun, this is the moon. He said that moon and the sun, they basically subtend a gravitational pull. Now, while this gravitational pull is nowhere so strong enough that it can stop or it can pull the planet to itself, but it is enough that as the planet rotates, it is able to hold on to one of the landmass as the landmass is freely floating. So imagine you have a landmass, it is moving along the planet, but because of the gravitational pull of the moon, this landmass is held in its own place and the planet continues to rotate underneath it. So he said that the tidal force holds the landmass as the planet rotates underneath. As a result, what will it appear? Suppose an individual, let's say Tom, is standing here, and that poor fellow observes that, look, this particular landmass, it is being held by the moon, rest of the landmass is moving in this direction, this landmass is being held here itself. So on the surface, what would you experience? You would experience a kind of a westward drift. So this was used to explain westward drift. Now ask yourself honestly, can this be possible? Do you think that this is something which is possible? Absolutely not. Absolutely not. Because if this would have been possible, if the sun and the moon would have had this significant amount of gravitational pull that it would exert, the planet in itself would have stopped rotating within 40 to 50,000 years, but it has not happened. So nowhere is the gravitational pull so strong that it will hold the landmass in its own place, right? So that is where basically the first reason that he provided, that was incorrect. Okay, so please understand, the reason that he provided, in his mind he could explain, but that was not the actual reason. What was the reason that he provided? He provided that gravitational pull extended by the sun and the moon, they are so strong that as the planet is rotating, anyways the continents are floating. So as the planet is rotating with the continents on top, while the moon cannot attract the planet to itself, it can certainly hold the landmass. And as the planet rotates, some of that landmass breaks due to that gravitational pull, and that is what we observe as the westward drift on the surface. So this talked about a strong, very strong gravitational pull. Gravitational pull. Obviously, this was an incorrect reasoning. Obviously, this is something which was false. Later on, it was proven to be false because that is simply not possible that the continents are floating. Nonetheless, the second reason that he provided in order to explain flight away from poles, so that is combination of centrifugal force and force of buoyancy. Guys, we will do this particular portion and then we will end the session. Okay? because otherwise it will be a tough ask on the next session. So, combination of centrifugal force and force of buoyancy. What is force of buoyancy? Force of buoyancy is anything that keeps something afloat. So when you have a water body, on top of it, why is it that the ship sails? Because you have a force of buoyancy which is applied. Force of buoyancy which is applied. If ever you want to experience that force of buoyancy, you would have observed that when you jump into water, you tend to rise up, right? So that is the force of buoyancy. If you have, let's say, a thermocol which is on a bucket of water, you try to press that thermocol to the bottom of the bucket, immediately it will rise up, it will float. Force of buoyancy. Now, because he said that the continents are floating, the continents are experiencing force of buoyancy. So as per Wagner, force of buoyancy was experienced. As per Wagner, this force of buoyancy was experienced by continents. Right? So that is what would keep them afloat. Now, on top of that, you had the centrifugal force. What is the centrifugal force? Any object which is moving in a kind of a circular motion, any object which is moving in a circular motion, now that object experiences a force away from the center. For example, if you have a ball and at the end of the that ball is attached to a string that you hold in your hand, if you start rotating that string with a significant velocity, you'll find that the ball eventually tends to have a force outwards. That is a centrifugal force, right? Now, on the planet Earth, where will the centrifugal force be experienced? So, there he took the help of the shape of the planet. Planet is not a perfect sphere. It is slightly bulged around the region of equator, and that is where he said that it is bulged around the region of equator. As the planet rotates around its axis from west to east, equator is slightly bulged, So, due to rotation, equator, the region around equator, experiences a centrifugal force in all direction. Due to rotation, region experiences a centrifugal force. Which region? The equatorial region. Equatorial region. That experiences a centrifugal force acting on the outside. Anyways, the continents are floating freely and they experience that force of buoyancy. Plus, that force of buoyancy keeps them afloat, right? And that force of buoyancy keeps them floating. That is what he assumed, that everything is freely floating. Add on to that the centrifugal force, which is acting on the outside. Now, that would mean that the continents naturally would be attracted towards the equatorial region. So, combined with the floating force, or that is the force of buoyancy, combined with the force of buoyancy, the continents would be driven to float towards the region where that centrifugal force is acting on the outside. Why only at equator? Because the shape of the planet is such, slightly flatter at the poles, slightly bulged at the equator. okay, towards equator. So that would explain his postulation that the continents, they are experiencing a flight or a movement away from the poles, right? Remember, he had to prove two kind of movements. One is to prove movement away from the poles, to prove westward drift. In order to prove westward drift, he chose the explanation of the tidal force. That tidal force is the gravitational pull extended by the moon and the sun. And then he chose the combination of centrifugal force and the force of buoyancy. Together, they would be acting on the land masses. And that is when the land masses, they would be driven towards the region of equator. Now, both these reasons, absolutely absurd, absolutely unjustified, and absolutely incorrect. First of all, the continents are not floating. As a result of that, they cannot be held by the tidal force. Anyways, the tidal force or the gravitational pull is nowhere as strong to hold the continents in their place. So the first reason is incorrect. The second reason, when you talk about it, now again the continents are not floating. There is no force of buoyancy acting on the continents. So there is no question of the continents being driven towards the region of equator because of this force of buoyancy. That is why, despite the fact that the evidences pointed to the drift of the continents, Wagner could not prove it. And that is why his theory was debunked. His theory of continental drift was rejected. But nonetheless, even while this theory was rejected, there was a lot of learning from it. There was a lot which was understood from it, and that later fructified when you had the evolution of plate tectonic theory. So you can say that the evidences indicated the studies done by Alfred Wagner that paved the way for the future generation theories. But nonetheless, due to faulty reasons and the faulty explanations he cited, his theory was rejected. Okay? That will be the end of the continental drift theory. And that is where we'll end the session here today as well. Okay? Now, because we have exceeded the time limit here, any questions that you have, our SMEs will be here to address the question. And Shivani, yes, you can make notes of the session. I hope that today's session was helpful to you guys. Some of it is understood. Revise this entire thing. We meet again next Saturday. That is when we'll continue with this and we'll carry out in the portion of plate tectonic, seafloor spreading, and convection current theory. So that will be all from my side. Till we meet again next weekend, take care of yourself. All the best. Goodbye and have a good night. Thank you.